you. Uh, okay, can you hear me?
Yes, sir.
Okay. So just give me a second before I start.
Sure, sir.
Yeah. Okay, so as I was speaking of different characterization techniques to understand the structure and the importance of structure, I'll continue on that endeavor. So now, uh, talking of spectroscopy, there are different types of spectroscopy, as I already explained, using X-rays, using electrons, using normal visible range, ultraviolet, infrared, and other. We are now moving into a short wave and already radio things and other things are available, right? Now, what we do actually to find out the electronic properties is to shine the samples with certain frequencies which which have the energy comparable with the energy of which is equivalent to the band gap of the materials. Okay. Now, those who are from electronics background, they quite well known, know it well. What band gap is? Band gap is the difference between the difference of energy between the conduction band and the valence band. And if you probe the material with a energy which can start from zero and go up to the band gap, then at the band gap you will have some absorption. I'll come to it later. So this is a basic setup that we have in our lab. It's a very small, simple setup. So this is a spectrometer, okay, and this is a source, and there is a fiber optics which is connected to this spectrometer, where the light comes from the source, falls to the sample, and from the sample holder it goes back to the spectrometer, and we can analyze it. So all UV visible spectrometer is basically works like that. So what it has a halogen lamp and a tungsten lamp, which provides a wide range of wavelengths, and then these fall on a reflector, and then it is dispersed using a prism or gratings, and then well, selectively we take the wavelength that we are interested in, and then we pass it through a reference sample and the detector and the sample itself. Then we have a ratio of this I0 and I, and then we get the absorption, which is with respect to the clean no sample. Okay, so this is how we can get absorption. Now, what does absorption spectroscopy actually provide in scientific uh, terms? So we know that there are states that are available in materials, and technically, if it is a perfect type of ideal thing, then the valence band will be populated by states, and there will be a sharp transition below which there will be states, occupied states, and then at a sharp point there will be no states anymore. And then the conjunction magic similarly starts from one point where there are no states, and then all of a sudden there are states. So if you combine these two things, so that the band gap is given by the difference of these two bands, and then we have if we do the absorption spectroscopy, if the energy is lesser than Eg, there will be no absorption, and at the band gap, when E is equal to Eg, then we have a sharp absorption. So this should be the absorption spectra, technically, ideally. But in real materials, it is not like that. So there are defects in the crystal, and that gives rise to some states which are which happen to be beyond this point. Beyond this point, I hope you can see my screen properly. So there was the valence band was supposed to be up to here, but there are states which are beyond this point. Similarly, the conduction band is also behaving like this. Changes the absorption spectra to something like this. Okay? Now, the absorption alpha at this point will behave as an exponential law. Okay, so alpha is equal to alpha 0 exponential E by some constant EU, where EU is generally known as the R-back energy. I'll come to it later on. Now, in a solid sample like zinc oxide, generally we prefer, if it is powder or something like that, we prefer to do diffuse reflection spectroscopy because it is not a transparent thing. So the light cannot pass through, like what I described in this slide. The light cannot pass through. So we need to change our setup, and we use a diffuse reflection spectroscopy, where we take into account that the absorption coefficient plus the transmission coefficient plus the reflection coefficient should be equal to 1, because that is the only three possibilities that can happen. And if it is opaque, then the transmission will be less. And we can say that the intensity of absorption will be proportional to 1 by R squared. Okay. 1 minus R whole square. Okay, that's the scattering capability will be 1 by R. So there are theories which can define this type of absorption thing, and the Kubilka-Monk function is one of them, and that is given by this 1 by R to the power square by 2R. So we calculate this Kubilka-Monk function, which is equivalent to the absorption coefficient, and we do the tau plots for a direct band and an indirect band, and try to find out what type of band it has. So from the linear part of this of this graph, where the absorption data is falling, we extrapolate this thing, and then we get the value of the band gap. So wherever this line comes down is the band gap. And this part is actually representing the exponential nature of the graph that I described here. Okay. Now, from this equation, alpha, if we take log of both sides, you can arrive at this equation. And this is a straight line equation. If you plot log alpha and h nu, then you will find that it has a slope which is equivalent to the R back energy. So from the slope of this log alpha versus h nu, we can get the R back energy, or the energy which is stored as disorder in the lattice. Okay. So disorder or defects, not defects, disorder in the lattice due to the structural deformations at the sites. Okay. Now, this is a typical zinc oxide, iron doped zinc oxide, and gallium doped zinc oxide absorption spectra. And you can see the band gap has increased as you go from iron doped to gallium doped. And as a result, the R-back energy has decreased. Now, why is this so? This R-back energy is related to disorder. So in this graph, if you reduce the disorder, you transit from this state to this type of thing. So the band gap, which was reduced, will increase. Okay. So this is a type of band gap tuning due to lattice disorder that is present in the samples. Okay? But apart from that, there can be other sorts of changes in the lattice, which can generate different types of changes in the material, in the band tuning. Okay, there can be different defect levels, as I told you. Now, suppose you dope something like 1+, like lithium in zinc oxide. Now you're thinking that lithium will go and replace zinc. Now zinc is, as I said, is 2 plus, right? But when you dope something with Li plus, that Li plus has a lesser charge than zinc. So what it will do, it will create some imbalance of charge in the lattice. So to encounter this imbalance, the lattice has to lose some negative charge. When it has to lose some negative charge, this change can come up as an oxygen vacancy. Okay, so for 2 lithium ions, we can expect 1 vacancy of oxygen. Now, then by doping more and more lithium, we'll create more and more oxygen difference. In generally speaking, in intrinsic zinc oxide means which is not doped, okay, pure zinc oxide also, due to the preparation technique, there are oxygen deficits which are found naturally. That is due to the lack of supply of oxygen at the time of creation of this lattice. Okay? Now, but the lattice cannot remain without oxygen all by itself because the charge, otherwise the lattice will be charged. That is not possible. So what it does, it compensates that loss either by putting another oxygen interstitial into the lattice, which can counteract for the oxygen defect, or it can create a zinc loss. So a zinc vacancy, okay. So we can create zinc vacancies, oxygen vacancies simultaneously, or oxygen interstitials, oxygen vacancies simultaneously. So these types of things can happen. There are other intrinsic defects that can be created due to the formation process. The oxygen may occupy a zinc site, which is called an anti-site disorder, or zinc may occupy an oxygen site, which is also called an anti-site disorder. So there are different types of donor levels and acceptor levels due to this creation of different types of mismanaged lattice. Okay. Now, like lithium, okay, I was okay. So now when remote access, I'm not sure who asked. Anyway, so yeah. So now when you do this type of thing, you have the chance that lithium will have its own states, right? Like in this case, here is an example where holmium 3 plus has been doped. When you dope holmium 3 plus has its own energy states. And some of these energy states are falling inside the band gap of zinc oxide. Okay, so these will contribute to different types of colors. Okay? Apart from that, there can be higher order colors that can be, means beyond the band gap, there can be other sources of excitement. Even luminescence. Okay. So all these types of defect states that are created due to doping or the intrinsic defects can be probed through something called photoluminescence spectroscopy. So what we do in photoluminescence spectroscopy is we excite an electron in the valence band to the conduction band to a state high enough to probe the defects, and then once the electron goes to that higher state, it can come back to the conduction band edge and then transit between states and give different colors of lights of different colors. Okay. Now there will be certainly one transition from the valence band, a conduction band to the valence band, and that will be somewhere near the band edge. That is it will be equivalent to the band gap. So that will give you an estimate of the band gap. So in zinc oxide, this intensity here near about 375 nanometer is corresponding to that type of near band edge emission, which is equivalent to the band gap. Okay. But apart from that, depending on the defect states, there can be a deep level emission, which is a broad hump-like structure. And generally in zinc oxide, we find different types of, we can fit this data with different, I think I have somewhere. No, I don't know that. We can fit this data with different peaks, Gaussian peaks, and different contributions corresponding to those energies that are allowed within the band gap can be justified to get the spectra, replicate the spectra. And that's how we estimate the amount of which type of defect is present in that sample. Okay, so by doing that, we can estimate the different defects that is available in it. Now, moving on from here, we need to know what the atoms are doing inside the lattice structure. A very important discovery then from our famous Indian scientist Sir C.V. Raman was Raman effect. Okay, the Raman effect is a way to understand the lattice vibrations or the phonons in a material. Okay, what are phonons? If you imagine the lattice to be small spherical balls coupled with springs in between each other, like this structure shown here. Then at a finite temperature, you have supplied some energy to the atoms and then they will start vibrating. Now, depending on the structural distribution of atoms and the spring constants of these springs, the vibrations will have different energies. Okay, there will be typical vibrations that can be decoupled into there is one set of vibrations that can describe the motion of these atoms. Okay, now these vibrations correspond to a set of different types of okay. So these different types of vibrations. Here you can see that they moving the oxygen and the zinc are moving opposite to each other. In this one, A1 LO and A1 TO, these are different modes. I will not go into this at this moment, but if someone is interested, I can describe it at a later point in a different class. Okay. So when these are vibrating opposite to each other, then the vibrations have changed. So all these modes will vibrate at a different frequency. Now, when you have this type of different frequencies, you need to probe them to understand how they are happening. So what Sir C.V. Raman did, he shunned the molecules with a definite wavelength of light. And what he observed was that there was the basic light was there, which has the same frequency or the same wavelength, that is the same energy. So it is an elastic scattering. And apart from that, there is one which has a larger wavelength and one which has a lower wavelength. So the lower wavelength, the lesser wavelength, he called it anti-Stokes, and the larger wavelength, he called it Stokes. What is the physics behind it? Let us find out. So when you excite the material with light, there is a state which is excited to a virtual energy state, and that state can decay to the same state, releasing the same amount of energy. That is the elastic scattering, which is also known as Rayleigh scattering. The other two, where the energy state is not the same of return. It can be a lower energy state. It can be a higher energy state. The lower energy state is a Stokes Raman scattering, and the higher energy state is the anti-Stokes Raman. Okay, so if the vibrational states from which it was started is not the same as where it has landed, then we get Stokes or anti-Stokes Raman scattering. Okay, from this we can know the energy of vibration that these molecules are having. Okay. So basically what we do, we put a laser, we focus the lens on the sample, focus the light on the sample using a lens, and then the light reflects or passes through it, and then we put a filter which takes away the Rayleigh scattering wavelength. This is a notch filter or a bandpass filter. And then we disperse the remainder of the light, and we get the Raman. Now, this is a typical Raman spectra, and you can see all the modes that I described here are seen here. And then we can deconvolute this Raman spectra into different specific Raman modes, which can allow us to understand which mode is more intense and which mode is less. Okay. So this is another setting. I am not going into that one. Okay, so you can see now. Let me. Okay. Now, what is happening in why this model is a valid model? Okay, why is a spring uh, used in this model? Okay, the spring has a force constant. Okay, now the spring has a force constant means it has a energy which is stored in the spring, and this is actually the equivalent to the bond strength between the atoms. Okay, so if the bond strength is more, the K value is more. If the bond strength is less, then the K value is less. Bonds, you must have studied springs. The energy stored in a spring is half kx square, where k is the spring constant and x is the deformation of the material. Okay, so that k is actually comparable to the bond strength of this atom. So now let us go back to our original refinement, where we did the ABC, we understood the lattice parameters, and it was also actually a way to look into the bond lengths. So now if we study the bond lengths and see that there is a change in the bond length, and we can correlate with the Raman properties, that is an excellent piece of information that we can get what happens when we dope materials with oxides or any materials with something else. Okay. So that as we get from simple harmonic motion of the oscillation of a ball, the frequency of the ball is proportional to k by m. So if the bond strength increases or the mass decreases, we expect a shift in the frequency, a blue shift. Okay, blue shift means it will become a higher value. The omega moves towards a higher value. If there is a move towards a lower value, either the K value has decreased or the M value has increased. So by doing this type of calculations or analysis, we can understand why a certain change is being observed. Not only that, there are theories which can calculate the strain in the which is inherent in the material. So when you dope something, you will put a strain in the lattice because, as I told you before, also that the strain, the ionic radii of this of the dopant is not the same. The charge of the dopant is not may not be the same. So suppose you put lithium, as I was saying, lithium as a 1+ state. How will it will interact with the oxygen, neighboring oxygen, is a matter of investigation. Is it increasing the bond strength? Is it decreasing the bond strength? What happens to the rest of the zinc oxygen bond strengths? All those informations can be obtained from this type of calculations. So Raman is a very powerful tool to understand the correlation of the lattice structure to the different types of motion of the atoms, and hence the electronic properties. Okay. Now, oh, sorry, I misplaced this thing. So this is the photoluminescence studies, which I already said, and this is the graph that I wanted to show you. There's this is a deconvolution of the different types of defects that are available, and from these analysis, we can grow the, you can plot the CIE, chromatographic index file, and we can say what is the luminescence, how the luminescence is traveling. Means here you can see the original pure sample was x is equal to 0 here. Then it has moved to a ray emission. And as you go on doping more and more, this has come to a white type of light emission. So you get a white emission from a yellowish, initially in a yellowish glow. So the entire luminescence of this sample has changed by doping. Now, as I said, that the oxygen vacancies are very well probed by luminescence. Okay, so we can see the green luminescence here. So even whenever we see green luminescence, we say, oh, okay, this material is deprived of oxygen. Whenever we see red luminescence, we said, okay, there is excess of oxygen. Okay, so there is more oxygen interstitial. Okay, so let me give an example. Suppose you have a pure zinc oxide, and you know that there is a green luminescence, so there are oxygen defects. The moment you put something which is higher in charge, like gallium, so gallium 3 plus, we have observed that by providing gallium 3 plus, immediately the luminescence changes from green luminescence to red luminescence. Because there are more, all the oxygen defects have been taken care of, because there is excess positive charge in the lattice. So it has to be compensated by reducing all the oxygen vacancies and bringing in more oxygen in the lattice. So oxygen interstitials are formed. So as a result, we have the orange-red emission. Okay. So here, the oxygen defects or the defect states can also be probed by doing electron paramagnetic resonance spectroscopy. It is These are all paramagnetic states, these defect states, and these can be probed by doing this EPR spectroscopy. Okay. Now, different defects have different types of G values, the Lange G factor. Okay, I'll come to this. Let me go to this slide first. Okay, so what is EPR spectroscopy? Okay, so every electron has a magnetic moment, right? And it has a magnetic moment, and it has a spin quantum number, which is half. So ms, the magnetic quantum numbers, can have plus half and minus half components, right? Now, in an external magnetic field B0, when you put a magnetic field, there is a Siemens splitting, and the energy of the states become msg, which is the Lange G factor, mu b, which is the Bohr magneton, and B0. So this energy depends on B0, right? The field. So the two states that we have are separated thereby by a value of G mu b B0. Okay. So now suppose you now try to perturb the state by using a photon. Okay. An unpaired electron can be in both these states. So if you perturb the system with an external photon, then what will happen? It can absorb that light, and if that light is equal to this delta E, then it will give you a change of state. Okay. So the resonance condition can be obtained if h nu is equal to the change of this energy. Now, this gives us infinite number of possibilities. Depending on B0, h nu will be dependent, because these two are constants for the thing, right? So how much field you are giving, that will determine h nu. Okay. Now, this delta G and mu B, these are properties of the material, right? So G changes with, as I said here, G changes with different types of defects, right? So by probing the different G values, we can think of, just give me 1 second. Sorry. Yeah. Huh. So by probing the different photon energies, we can types of B values. So generally, the trend is to put a definite amount of in field strength, and that is about 0.35 Tesla, and then see at what frequency has a resonance. Okay. So this is a very conventional thing, and then we can find out the value of G from these the values. So whenever there is a absorption, we get a resonance, and we do the first derivative of this thing, and we can precisely find where the absorption is taking place. Okay. Now, from here, we check the next thing that we check is the transport property measurements. Okay? The transport property measurements is a very important thing that is important in all types of semiconductors, and that is done by using a Hall probe measurement. Okay, the Hall probe measurement is nothing but we take a semiconductor and apply an electric field along this direction. That means we drive a current through it. And when a current is flown through this material, the electrons will be flowing from the positive terminal to the negative terminal. And if there are holes, then the, electrons will come from the negative terminal to positive terminal. If there are holes, then it will come from the positive terminal to the negative terminal. Okay, so the direction of propagation of these holes and electrons will be opposite to each other, but the current will still be along from the positive direction to the negative direction according to the convention, right? Now, the current is along one direction, and if you apply a magnetic field now in this direction, okay, then what you will find, there will be Lorentz force on the acting on these carriers, and there will be a deflection due to the Lorentz force. Okay, and the deflection will deflect the particles along this direction. Okay, the force will be on the same direction, but because of the difference in charge, the potential developed due to this deflection will be different. Okay, as a result, the Hall coefficient will be positive or negative depending on the nature of the the carrier. Okay, it will be positive for the p-type carriers and negative for the electrons. Okay? Now, here is a classical example of where we found that the Hall coefficient has changed. See, this is 0, right? This line is 0. So initially it was negative in value, and then it went up to a positive value. Okay, the RH value became positive. Now, such a thing can be verified by sandwiching two N-type and P-type materials. This is the one of the classical examples done in our lab, actually. And we could find that a zinc oxide, which is a negative Hall effect, Hall coefficient, which has a negative Hall coefficient, and the gallium doped ones, which has a positive Hall coefficient. They were sandwiched together, and we found a perfect PN junction type behavior in this material. Okay? Now, the mobility factor, the conductivity are all derived from these electrical measurements, and that gives us an idea how the dopant has changed the material's transport properties. Okay, here you can see that the sigma value has changed. That is, the conductivity, DC conductivity has changed. It has improved drastically, actually, and also the mobility factor has also improved drastically in this 3.1, say 4.5% dope gallium dope zinc oxide. Okay, so it is a very important study, and it is needed for all materials that we prepare in our lab. Okay, now this is something very important. Okay, so what happens actually when we dope material, when we dope different elements? Okay, now this is a classic example of nickel and gallium dope materials. So we can see that in the nickel doped materials, so this is something called electron localization function. This is not an experimental technique of doing it, but you remember we said that the Rydberg refinement gives us an opportunity to find the structural details of the material. The structural details is contained in a file which is called a crystallographic index file, CIF file. So the CIF file contains the lattice positions that the constituent elements are occupying. It can be zinc, it can be oxygen, it can be nickel, gallium, whatever you have doped. They have a coordinate with respect to the lattice, the unit cell that we have described. Okay. Now, if we put this zip file into a simulation process to understand how the electronic properties are changing, we can find out how the electrons get localized along a dopant molecule element. Okay, so here we can see that the electron configuration is very less along a nickel ion. Okay, so that means the entire cloud of electrons is concentrated on the oxygen, neighboring oxygen, and we get no electrons. The distribution becomes very less. So the electron is not available for transport when we dope it with nickel. But for a gallium, the availability of the electrons is much more better. This graph, this maybe it is not very clear from this graph, but the numerical analysis that we have done clearly mentions this type of thing. Okay? So by doing this type of analysis, we say that the electrons had got confined, localized at the nickel side, but at the gallium side, it has become more open. Now, when we do such changes in the structure, not only the electronic properties give us some electronic functionality or electronic in some electronics like application, but it also affects the material's hardness. Why? Because, as I said, the bond strengths are being affected, right? When the bond strengths are being affected, it is very natural that we will find that if the bond has become weaker, it will become weaker, means less hard material. If the bonds have become stronger, it will become a better hard material. Okay, harder material. Okay, so this we can test by putting some probe like this conical shape load. We can push it down, and by finding out how much it has penetrated to the surface, there's a zero reference line. From that reference line, how much this indentation has been made. By calculating the diagonals of this indentation, we can find out the hardness of this material. Okay, this is a non-destructive testing of bulk material of this type of things. We have done some experiments on that, and we found that and the theoretical hardness that can be calculated from these things are associated with different energies, the homopolar energy, the heteropolar energy. These energies come from the distance between the bond lengths and other aspects correlated to the structure. And from those structural points, we can calculate the bulk modulus and other and then correlate with the actual data that can be found out. So this is a direct correlation between the experiment and. Now, as I said in the preliminary or the part one, that by pressurizing the Wurtzite structure, we can get a rock salt structure. Now, even if we do not go to that extent, what are the other changes that we can expect from this type of structure if pressure is applied to these materials? When pressure is applied to these materials, obviously there will be some change in the angles, and there may be some change in the bond length also. Okay, even if we do not put the rock salt structure, even within the perspective of the Wurtzite structure, certain changes, subtle changes will be expected in these results, right? Okay, so what you have done, the best way to look into the changes is to do a normal current versus voltage measurement to see whether the electron's mobility factor or what is changing actually. Okay. See, we cannot change the carrier concentration here. So the only change that can be done is the how easily or how more difficult the electron can get chance to be transported. Okay, that's a mobility factor. So the chance of hopping from one side to another, how much easier or difficult it is. So we measured the current for with different applied voltage, and from those we found out that the current actually increases with iron doping. Okay, with the application of pressure. Okay, so this is the applied pressure, and when you apply the pressure, the current has increased. So you are facilitating the transport property by the application of this pressure. So this is a direct correlation of pressure and the transport. Now, what are the functionalities that we can watch? In the beginning of the slides, I showed some data on the photosensing. Now, the photosensing is a very interesting thing. This is a homemade setup that we developed in our lab. It's a very simple setup. We need a Kitli 2450 source meter, an Arduino setup here. This is the Arduino, and which can control the light to be on and off. And then some light sources, different light sources are used. And then the intensity meter is needed to see how much intense light is falling on the sample. So we made the setup for 4 different colors. We can make more, probe more frequencies. And what happens actually? So when you turn on the light, the electrons are transported from the valence band to the conduction band. As a result, an electron hole pair is generated, and these pairs actually take part in the sensing process. So when the frequency of light, the light interacts with the oxygen, it creates an electron hole pair, as I already said, and it transforms the gaseous oxygen to a radical, which is called the adsorbed oxygen radical, and that has a negative charge. And then this adsorbed oxygen, due to this negative charge, gets stuck to the surface of the zinc oxide because it has a hole there. Okay, so it gets attracted and it gets stuck. Now, when the light is off, the adsorbed oxygen and the hole, they exchange the charge, and the oxygen gas is liberated. Okay, so when this type of thing happens, the current goes up. In the presence of the light, the current goes up because the electronic transport has taken place. And then what happens? When you turn off the light, then it decays. Now, what we have done, as you can see, there's a exponentially growing light. So we have fitted this light, this current, with 2 different exponential terms. We tried to fit with one, but it did not fit well, saying that there are 2 processes, a fast process and a slow process. Okay, so there are 2 processes involved in this. So there are 2 origins of the defect states, or maybe the band-to-band transition, which can take part in zinc oxide. In copper oxide, we found that there is only one process. But in zinc oxide, we have tried different samples, but we cannot feed it. So these are the ways we can assess how many processes are taking place in a phenomenon. Okay, and from that, we can find out how the fast process is changing, how the slow process is changing. See here, the fast process actually became very slow. Okay, it started from about 2 seconds, and it became about 16 to 17 seconds. Okay, 17.5 with doping, right? And then it became faster again. And it has to do a lot with the electronic structures. This can be correlated with the lattice strain and other things. Those are all internal things that we have to assess. To write a paper, to do analysis, we have to see what is determining what. Okay. And on the other hand, you can see the slower process. It was a very slow process at the beginning, and that has actually become very fast. Okay, this has become very fast. So the entire process is. So we can check on all these parameters and what is the component of the current that is being changed. So these parameters are. We can also calculate the sensitivity of this material to light and see how these things are changing. Okay. So now, I have 15 minutes, right? I have to go a little bit faster. Okay. So occasionally what we see that a material by itself may not be a very good sensor, but when you make a heterojunction with something else, it forms it has a very fast way of responding to the light. Okay. Here in this is an example where we have doped lithium doped copper oxide. When you put sandwiched lithium doped copper oxide with zinc oxide, and this device has become very fast. You can see the tau has become 17 seconds instead of 129 seconds for the normal copper oxide and the normal the lithium dope. So just by sandwiching it with zinc oxide, it has become. And that is because you have facilitated the electron transport. If you look at the band gap, this is the band gap of zinc oxide, this is the band gap of copper oxide. So when you excite the electrons, a hole and an electron is created. Immediately the electron can be transported from here and the hole can be transported. And we get current. Apart from that, we do a little bit of photocatalysis. This is a homemade photocatalysis setup. We use the same UV visible spectroscope to do this type of experiment. There is a source, there's a container which contains the dye. Dye degradation has become a very important sociological problem right now, because water bodies are getting affected by harmful dyes, which are eliminated from dye industries and other things, and cloth textile industry especially. And they go into the natural water bodies, and then they create a lot of nuisance. So we need to find out an answer how to degrade this dye. So one of the ways is photocatalysis, and then it needs some material. So we have tried with zinc oxide, we have tried with copper oxide, we are presently working on nickel oxide and copper oxide combinations, and lot more. Okay. Now, what is interesting is this type of setup can be very easily made in our lab. In the lab, if we have a basic UV visible spectroscope like this, we can do this at home. Okay. So the dye actually, how it is degraded. Okay, so again, the electron hole pair is created, and the electron affects the oxygen. This oxygen radical goes, and this is the dye itself. It can affect the bridge bond that is here, and this bond can be ruptured, giving rise to two different ways, and the bond is cleaved, and then the cleaved materials also, they decompose into simpler entities like water vapor and carbon dioxide. Okay, so these simpler entities do not harm the environment. So this is a very important thing. Methane blue is an example here, but we have worked with other dyes also. Okay, now the dye degradation is generally, see, this is the spectra, and you can see the spectra goes down with time. And if you calculate the degradation rate, the degradation rate is the concentration is directly proportional to the absorbance of the material. So if the absorbance is going down, then actually the concentration of the MB dye or the dye is going down. So you can correlate to absorption. So CT by C0 is equal to AT by A0. And then you can calculate the degradation rate using this formula. Okay, so this is the degradation rate, and you can see the degradation is about 30% in 180. This is not a good example, but for other materials that we are working right now, zinc oxide is not a very good dye degrader, but titanium oxide is, copper oxide is, nickel oxide, yes and no, depends on what you're doing. Okay. So apart from that, there are electrochemical properties that we measure that can be measured on zinc oxide and other materials. And this is one of our published papers from Journal of Applied Physics. And there are Faraday reduction, oxidation reduction processes involved when you do this type of cyclic voltammetry experiments. And we can this originate for the intercalation and deintercalation of alkali metal. It can be sodium, it can be potassium, in some electrolyte. You have to choose your electrolyte properly, and the zinc oxide. Okay, so what happens? The potassium gets attached to the zinc oxide nanoparticles use with the electron being added to it and subtracted from it, and we get this type of behavior of oxidation. Okay, from these graphs, what we can get, we can calculate the specific capacitance, and we can see that the specific capacitance of these materials actually depend on a lot of things. Say, this is a aluminum doped material, a zinc oxide material, and this is a purely lithium doped. What you have done here, we have changed the proportion of aluminum and lithium in these different samples, and we have seen that for a mixed doping of aluminum to lithium, where aluminum is 75% and lithium is 25%, we have maximum specific capacitance. And these are due to the combined effort of the lithium 3 plus and the lithium 1 plus and the aluminum 3 plus. So why did we go for 3 plus and 1 plus? You know, zinc is 2 plus, right? So we tried to find out what is the effect of a combination of these 3 plus and 1 plus. If it is 50-50, then 3 plus and 1 plus makes 2 plus, an average of 2 plus. Okay? So now, how does the charge of the dopant affect this type of behavior? And we found that it is very important that when we do these type of experiments, maybe this is not the 3 plus or the 1 plus, it is somewhere intermediate, where the specific capacitance, which can be used in different charge storage devices, is maximum for a mixed material. Now, recently, in the last 1.5 years, we have started making thin films in our lab. This is a sputtering process. In sample preparation, I started with sol gel. So we make modified materials using sol gel synthesis route. And with that, if the material is interesting, then we make a target of, say, 10 grams of this material and make it into a small pellet of 2-inch diameter, and we use it as a target material. And what we do, we put a very high potential between a substrate on which we want the thin film, and this high potential, the RF potential, actually strips off the atoms or molecules from the target material and deposits that this is a plume of the molecules that are stripped off. There's a plasma actually, and you can see the plasma there. It has a shape here. The plume has a shape here, and if it is very hard to notice here, but there's the substrate is here, so the atoms travel all the distance and get deposited on the substrate. Now we sometimes apply temperature on the substrate to make the thin films more better. Okay. And you see there's a thin film, somebody is holding, and it's a transparent thin film. So you can use light to see, it can make a solar cell out of this and whatever light sensitive device you want to make. And then there are electrodes that has been deposited to find out this thing. So we are now working on these things. And before I end, I want to introduce my group. This is a long time pictures. This is my first batch who have, all of them have left now. None left. And this guy defended his thesis just 2 days before. He has submitted his thesis, and I want to acknowledge Surya Scan Bihar University for kindly inviting me to give this lecture, and especially Professor Ankur Jain. And also, I want to, before I end, I want to thank IIT Indore and DST AMT for funding my research and other aspects of my research programs. Thank you. Before finally, one note, those who are listening, I hope you will become a good scientist, discover new materials, and help our country and the world to be a better place to live in.
Thank you so much, sir. Thank you so much for your wishes. I hope our participants, they have received a detailed elaboration on this topic, and it was such a nice informative session. Sir, I want to take questions from the chat box.
Sure.
Yes, sir. Sir, our first question is from Dr. Meenal Bafna, and she's asking what information is exactly obtained from Raman spectroscopy and how this information is different from the information that is obtained from the FTIR spectra.
Okay, very good. Okay. So FTIR and Raman are mostly complementary to each other. Okay, so the vibrational spectra, they can be probed, but okay, let me go to the, okay. So in FTIR, what we do, we shine the material with a direct light, which is in the IR range, which can correspond to the this is infrared absorption. I've written it here. So the infrared absorption means it's the FTIR. Okay. Now there's a physics behind it, and which says that both of these things cannot go simultaneously together, but it is not absolutely correct. We have found in many cases that FTIR and FTIR and Raman can be done on these samples, on the same sample. But basically, it gives the different phonon modes. In some, if you look into group theory, then some modes are Raman active and some modes are not. Those who are not active, they can be obtained from FTIR. Okay. So this is the only difference between, but we all probe the different vibrational modes using these two.
Thank you, sir. Meenal madam is also asking that if it is possible for you, can you please share the samples, example of the samples exhibiting the ESR and EPR responses?
Sure, I will do that. I'll do that later on. Yeah.
Okay, sir. The next question is from Ms. Mamta Patel, and she is asking, in Raman spectroscopy, which software we are using currently in Indian context, and what can be the forensic applications of it?
Oh, forensic application is a very important thing. Okay. First of all, Raman spectroscopy is a very interesting thing, but it requires a lattice to vibrate. Okay. If the if the material that you are investigating is not in a regular crystalline lattice, then it is difficult to get a Raman spectroscopy. Okay. Although it is used to find out some crystallographic components in the forensic elements. Okay. But it's not guaranteed that you will find a Raman spectra from all materials. Okay. It's very difficult. Okay. Now, software is not very important because once you get the data, you can try to deconvolute. I don't think I have a Raman. Okay. Yeah. So this type of deconvolution can be done very easily done by using different Gaussian or Lorentzian or a combination of those type of peaks like white peaks and other things. Okay, any software can be used like Origin, FitYK, anything can be used, okay, to fit the data. And then you can, but that fitting has to be very qualified fitting, because if you do not expect a frequency at that point, then it becomes problematic for you to understand what it is. Okay. So suppose you are doing a forensic test, you must be expecting some components in that forensic test. Okay. So suppose you see the victim has got some traces of something. Okay. So you have to do a Raman spectra of that thing, and then the object that you are investigating, you have to go to that object and find whether that same signal is being present in it. And then how much is the quantity of which component that there will be several components, maybe one or two different other things from the from that person who has done the guild. So those components has to be separated out, and then you have to get to a result.
Thank you so much, sir. Next question is from Ms. Ramya Nair. And she's asking, can you please explain that homemade setup in your lab for spectroscopy using Keithley source meter that you have just shown in your slide?
Sure. Okay. So this is the Arduino, as I said. Okay. And this is the power supply to 4 different light sources. Okay. Now, this Arduino actually turns on and off. We can write a program in a computer, and then we can turn on the light at this moment. And then after a certain interval, we turn off the light and then again turn on the light. So this sequence is controlled by the Arduino. And then there is a light source, which is connected to this source. And then by controlling it from the computer, we can switch on and off. And the Keithley source is just setting a voltage across the electrodes, and the light is when it is falling on the sample in between these 2 electrodes, we are measuring the current only, and that's it. It's very simple thing.
Thank you so much, sir. One last thing is, our participants wants you to share your email ID or any contact info, sir, if it is possible, so that they can contact you in case they require any future guidance.
Okay, so how do I do this? Because I do not know. Now I stop sharing.
So you can write in chat box, sir.
Chat box. Where is the chat box? Yes. Okay. Okay. SENS. Yeah, this is my email ID. Okay.
Thank you so much, sir. Sir, on the behalf of Gyan Bihar University, I want to express our hearty gratitude that you took 2 sessions today and you explained so many technicalities of different characterization techniques. And I hope they all will be so much useful to our participants. So thank you so much, sir. Thank you so much, everyone, for joining these sessions. And for tomorrow, you will get shortly an email regarding the session details. So thank you so much, everyone, for joining.
I want to thank Professor Jain for giving me this opportunity. Thank you, Professor Jain.
Thank you so much, sir, on his behalf.